The topic of today's lecture is basic electricity. I will discuss the basic quantities that relate to electric current, electric charges, and Ohm's Law, and also will explain how to analyze simple, parallel, and series circuits. Electricity was first discovered, or some properties of it were first discovered by the ancient Greek. They found out that pieces of amber, when held in pockets, would attract small pieces of lint or clothing fiber or dust due to friction with the fabric of their clothes. Due to the lack of proper technology to investigate this phenomenon, the knowledge about electricity did not improve for the next hundreds of years until the Industrial Revolution, where people found out that electricity can be transferred from place to place by metal conductors. People also found out that other types of materials do not conduct electricity at all. So those materials are known as insulators. So materials that conduct electricity, as I already mentioned, are metals, and the most common ones that are both that are very good at conducting electricity are gold, platinum, silver, and the more cost-effective ones are copper and aluminum. Materials that do not conduct electricity are rubbers, plastics, glass, and ceramics, and also wood. Electricity is carried by electric charges. To understand electric charges, let's look at the building blocks of matter, which are the atoms. Each atom consists of a nucleus, which has two types of particles in it, the protons and the neutrons, and then electrons, which orbit around the nucleus in a sort of a cloud of electrons. The protons are positively charged particles, the electrons are negatively charged particles, and the neutrons do not have electric charge. So depending on the particular material or element, the number of protons and electrons varies for the atoms of that element. So when we have a lot of electrons that orbit around the nucleus, the rules of nature prevent more than 2 electrons per orbit. So many electrons orbiting around the nucleus will have to spread over orbits with different radius. And some of these orbits have very large radius, which means that the force with which the electrons are being attracted to the nucleus is very small, and those electrons can easily leave the atom and just float around between the atoms of the material. Those are known as free electrons, and they carry the electric charges. The protons, even though they're charged, they're fixed in the nucleus of the atom, so they do not move around. So the electric charges carried in metals are carried by the electrons. The charge of one electron is considered to be negative, and the magnitude of this charge is 1.6 times 10 to the negative 19 coulombs. The charge of a proton is considered to be positive, and the magnitude of that charge is 1.6 times 10 to the negative 19 coulombs. Coulomb, who was a French physicist, was able to derive a relationship that calculates the force of interaction between electric charges, or in general between charged objects. He also was able to determine that objects that are charged with the same type of charge, either both positive or both negative, will repel each other, and objects that are charged with opposite charges will attract each other. And so the general rule states that like charges repel and opposite charges attract. So the statement of Coulombs Law, the law that calculates the electric force between charged objects, is as follows. The force between 2-point charges, Q1 and Q2, is directly proportional to the product of their magnitudes and inversely proportional to the square of the distance separating them. Written as a formula, this reads as the electric force of interaction between two charged objects is equal to the product of the electric constant K, which has value of 9 times 10 to the 9th newtons meter squared per coulomb squared, times the charge of the first charged object times the charge of the second charged object divided by the distance between the two charges to the second power. So if I sketch the picture of two charges in space, that could look like this. A positive charge, Q1, a negative charge, Q2. The distance between the two, let's call it R. So these two, since they are opposite charges, will attract each other. So the force with which Q1 acts on Q2 is F, and is directed towards Q1. The force with which Q2 acts on Q1 is also F, and is directed towards Q2. So when I calculate the force of attraction between the charges, the force of interaction between the two charges F, this force is the same for either charge. It is not shared based on how big each charge is. It is the same for both charges. Okay, so now let's address these quantities, the charges and the distance in numbers, and let's calculate the force of interaction. So the positive charge is 6.5 microcoulombs, and the negative charge is 3 microcoulombs. The distance between the two charges is 0.2 centimeters. The question is, what is the magnitude of the force between those two charges? So here is the formula for the force between the charges. The constant K, the electric constant K, times the charge of the first object times the charge of the second object divided by the distance to the second power. The constant is 9 times 10 to the 9th Newton meter square per coulomb square. And then I must multiply the two charges. However, notice that the charges here are presented, the values of the charges are presented as prefixes, and we cannot calculate with those. We have to convert them into powers of 10. So the prefix micro corresponds to 10 to the negative 6th power. So I will replace micro here and here with times 10 to the negative 6th power. So the first charge will become 6.5 times 10 to the negative 6 coulombs. The second charge will be 3 times 10 to the negative 6 coulombs. Also, notice that in this electric constant, the length unit is in meters, but the distance between the charges is presented in centimeters. So therefore, this length must be converted into meters as well. So 0.2 centimeters is equal to 2 times 10 to the negative 3 meters. Now putting everything together in the formula here, I get 9 times 10 to the 9th Newton meter square per coulomb square times 6.5 times 10 to the negative 6 coulombs times 3 times 10 to the negative 6 coulombs divided by 2 times 10 to the negative 3 meters to the second power. So coulomb squared here will cancel with those coulombs from the charges. When you square the meters here in the denominator, that's going to cancel with meters squared right here. And when you calculate the result, you get 4.3 times 10 to the 4th newtons, the only unit that's left, and that is the force between those two charges. So now that we have discussed the charges that carry electricity, we know that these charges, if we want to move them from place to place, we must give them some energy, right? So the electric force that acts on those charges makes them move faster or slower as they move through space. So essentially, their kinetic energy changes. So these charges, in other words, carry energy. Okay, so this energy can be used for various applications, such as generating light, generating heat, or converting into a different kind of energy. So in order for that to happen, we need to have a device that is capable of transporting these charges from one place to another and converting the energy that these charges carry. So such a device is known as a circuit. So let's look at simple circuits, the most basic ones. A circuit needs three main components in order to function properly and be able to extract the energy carried by electric charges. A circuit needs a source of energy, which would be either a battery, a solar cell, electric generator, or the power grid. So the source provides the energy that the electric charges will carry around the circuit that will be used for various purposes later. The charges also need a path along which they will travel, and that is provided by the conductors in the circuit. The conductors in the circuit, also known as wires, are made from metal, and so electrons can fairly easily travel through the wires to carry the energy to its destination. The most common materials for the wires in a circuit are copper and aluminum because they're cheap enough to use and provide good electrical properties. Other materials that are used in more specific circumstances are gold, platinum, and silver. Finally, the energy that's carried by the electric charges is used by the load, which is connected to the circuit, and the load would convert the electrical energy into different forms of energy or work. Examples of load in a circuit would be light bulbs, electromotors, a cell phone connected to the power grid to charge, and so on and so forth. Now let's look at some important properties and quantities related to the operation of electric circuits. Let's talk about electric current first. If you take a look at electric wire, which is not connected to a power source, what you will find is that the atoms of the material from which the wire is made form a symmetric, periodic structure, which is known as crystal lattice. And so the atoms here are these orange dots. The electrons that hop off atoms and move around freely are the free electrons, those are the blue dots, and they move in random directions inside the wire. So overall, the electrons do not really move in the wire at all. If both ends of the wire are connected to a power source, for example a battery, that is going to then generate electric force in the circuit, and the electrons will want to move away from the negative terminal of the battery towards the positive terminal of the battery. So a flow in a particular direction is created for these electrons. This flow is known as the electric current. So how can the electric current be calculated in a circuit? Well, if this is the wire in which the electrons flow, if I can count the amount of charge that flows through a cross-section of the wire for some amount of time and take the ratio of the charge to time, that will give me the electric current in this wire. So the electric current is defined as the amount of charge that flows through a section of the conductor per unit time. The current I is equal to the amount of charge divided by the time it took to flow through that cross-section. The units for current are amperes, and 1 ampere is equal to a charge of 1 coulomb flowing through a section of the circuit or the conductor in 1 second. So charges are moving in the circuit under the action of electric forces provided by the power source that is connected in the circuit. But we know from before that if force is applied to an object and this object moves certain distance, then that means that work was done on the object. So when charges move in a circuit, work is being done on these charges by the electric force. The reason why work is possible to do work on the charges is that when the power source is connected to the circuit, a difference in potential is created in the circuit. So this potential difference is calculated as the work done to move a certain amount of charge between 2 points in the circuit divided by the amount of charge that was moved. The units for potential difference are volts, and 1 volt is equal to 1 joule of work per 1 coulomb of charge. So for example, if you look at the 1.5 volt battery, that means that 1.5 joules of work would be done if 1 coulomb of charge is moved in the circuit to which that battery is connected. Finally, the third component that is important for the operation of an electric circuit is the resistance of the circuit. We label the resistance with capital R. The resistance of a circuit or a wire depends on several different factors. The first one is the length of the wire. As the length of the wire increases, so does the resistance of the wire. So the longer the wire, the larger the resistance of the wire. Why is that? Well, the material is made from arrangements of atoms, and we have free electrons that move around in the wire. But when the length is larger, that means that there are more atoms to which these free electrons can latch on, which then decreases the amount of free electrons available, which is essentially a decrease in the current in the wire. When the wire is shorter, there is less atoms to which the electrons can get stuck. Therefore, more electrons can pass through that wire, so higher current can pass, less resistance. Another factor that affects the resistance to current flow is the cross-sectional area A. So for the same amount of current that passes through two wires, a wire that has small cross-section area will be more resistant to the current flow compared to a wire with larger cross-section area. Why is that? Because when the cross-section area is small, we have a certain amount of electrons that want to pass through, but they have less space to fit in. So therefore, higher chance for these electrons to get caught by an atom that has a vacancy for electrons. When the cross-section area is large, that same amount of charge will pass through much larger space, so therefore there is less chance for electrons to be caught on atoms. So as the cross-section area increases, the resistance decreases. And finally, another factor that affects the resistance of a wire is the material from which the wire is made. More specifically, that is the resistivity of the material, which we label with ρ, the Greek letter ρ. The resistivity of a material is a function of temperature. When the temperature of the material rises, the resistivity also increases. When the temperature of the material goes down, the resistivity decreases. And so, as the resistivity increases, the resistance will increase. The resistance will increase. As the resistivity decreases, the resistance will decrease. And the resistivity increases when the temperature of the material increases. And the resistivity decreases when the temperature of the material decreases. So combining the three components, length, cross-section area, and resistivity, together calculates the resistance of a wire based on those physical parameters. So the resistance of a wire is equal to the product of the resistivity, the length of the wire, and we divide that by the cross-section area of the wire. The three quantities, potential difference, electric current, and resistance, are related through Ohm's law. So Ohm's law states that the potential difference in a conductor is equal to the current that passes through a conductor times the resistance of the conductor. From here I can rearrange the terms to get expressions for the current and for the resistance. The current is equal to the potential difference divided by the resistance of the current of the circuit. The resistance is equal to the potential difference divided by the current in the circuit. Ohm's law in this form can be used to analyze circuits. And there are two types of circuits that are the main types: series and parallel. From those two types of circuits, when they're combined, we get what's known as compound circuits. So let's see how Ohm's law is used to analyze series and parallel circuits, and then I will also conceptually explain how compound circuits are analyzed. So first, before we start, let's talk about the schematic representation of a circuit. So on the left side here, you see a simple circuit which consists of a battery, two wires, and a light bulb. So this is the power source, these are the conductors, and this here, the light bulb, is the load in the circuit. Even this simple circuit is not necessarily easy to draw. However, we can represent the different components in the circuit with schematics or schematic representation, which makes it then easy to draw circuits. So the power source is represented by two parallel lines with different length. The longer of the two is the positive terminal, the shorter of the two represents the negative terminal, and the label for the power source is either a V or an E. The wires in the circuit are presented with solid lines, and the load is presented by its resistance R, and therefore the load is also known as a resistor, and it's either represented with a solid bar or a zigzag line. Now let's look at a series circuit and see how Ohm's law is applied to analyze that circuit. So in a series circuit, we have the power source, and then the three loads or resistors are connected one after the other, as shown in this schematic, starting with the first resistor connected to the positive terminal of the power source. Then the free end of the first resistor is connected to the second resistor, the free end of the second resistor is connected to the third resistor, and then the free end of the third resistor is connected to the negative terminal of the power source. So the first important quality or property of this series circuit is that all currents in the circuit are equal. So the current that is generated in the circuit by the power source is equal to the current that passes through each of the resistors. So the total current I generated by the power source is equal to the current in the first resistor, is equal to the current in the second resistor, is equal to the current in the third resistor. All currents are equal. But because the resistances of those resistors are different, that means that the voltage drops across each of those resistors are different. But it turns out that the potential difference between the terminals of the battery is equal to the sum of voltage drops across these resistors. So the potential difference between the terminals of the battery is equal to the sum of voltage drops across each resistor. Finally, this circuit, which has three resistors in it, also can be represented by its equivalent resistance or total resistance, which is calculated from the resistances of the individual resistors. So for a series circuit, the total or equivalent resistance R is calculated as the sum of the resistances of each resistor. So these relationships here gives us the total current in the circuit, the potential difference between the terminals of the power source, and the total resistance of the circuit. These three can be related with Ohm's law for the entire circuit. But I also can use Ohm's law to find the relationships between currents, resistances, and voltage drops for each of the resistors. And so I can write Ohm's law once for the entire circuit, where the potential difference between the terminals of the battery is equal to the product of the entire of the total current in the circuit and the total resistance in the circuit. Or I can write Ohm's law for each resistor separately, and then I get that the voltage drop across the first resistor is equal to the current in the first resistor times the resistance of the first resistor. And here for the calculation I can also use the fact that the current in the first resistor is equal to the total current in the circuit. Similarly, I can write the expressions for the second resistor and the third resistor, and again the currents in those two resistors are equal to the total current in the circuit. So applying both Ohm's law for the entire circuit and for the individual loads allows me to find all parameters of the circuit that a question may ask. Now let's discuss parallel circuits. So here's an example of a parallel circuit. Power source is connected to three resistors. The resistors are connected to the power source, so one end is connected to the positive terminal and the other end is connected to the negative terminal. So the potential drop across each of those three resistors is equal to the potential difference supplied to the circuit by the power source. The potential difference from the power source is equal to the voltage drop across each of the resistors. Now, because the resistors in general are different, the current that's applied to the circuit by the power source is not going to be equal in each resistor. So when the current reaches 0.7 right here, it's going to split. Some of it is going to go through resistor R1, and how much depends on the resistance of that resistor. What's left is going to continue to the next junction at 0.6, where it's going to split again. Some of the current is going to go through R2, the rest through R3. The currents in R2 and R3 are going to combine at 0.3, and then the current in R1 is going to combine with those two at 0.2 to produce again the total current in the circuit. So that means that the total current in the circuit is the sum of the currents that go through each resistor. So the total current in the circuit is equal to the sum of currents in each resistor. Finally, the resistance of this circuit can be calculated from the resistances of the individual resistors. So the total resistance can be calculated using the formula 1 divided by the total resistance is equal to 1 divided by the resistance of the first resistor plus 1 divided by the resistance of the second resistor plus 1 divided by the resistance of the third resistor. But there is a different formula that can be used. And this formula is that the resistance R is equal to 1 divided by 1 over the resistance of the first resistor plus 1 divided by the resistance of the second resistor plus 1 divided by the resistance of the third resistance, and so on and so forth if there are more resistors added to the circuit. So that Ohm's law can be combined both for the entire circuit and for the individual resistors and used together to find all the parameters of the circuit. So Ohm's law for the entire circuit reads that the potential difference applied by the power source is equal to the product of the total current in the circuit and the total resistance of the circuit. And for the individual resistors, Ohm's law is written as V1 is equal to I1 times R1 for the first resistor, then V2 is equal to I2 times R2 for the second resistor, and then V3 is equal to I3 times R3 for the third resistor. And you keep also in mind that the voltage drops across each resistor are equal to the potential difference applied to the circuit by the power source. Combining the two types of circuits together results in what's known as a compound circuit or compound circuits. And this is an example of such circuit. So the resistors R1 and R5 are connected in series to the power source, and then resistors R2 and R34 form a parallel branch in that circuit. So the general method of dealing with those types of circuits is to replace the parallel branch with one resistor, which corresponds to the total resistance of the resistors in the branch, and then treat the entire circuit as a series circuit from where you can find currents, voltage drops, or resistances if you need to. Then go back to the branch and use the previously found information to find currents in those resistors. So this compound circuit can be replaced with this series circuit, where R234 is the total resistance of R2 and R34, which is calculated using the formula from the previous slide that I showed you. R234 is equal to 1 divided by 1 over R2 plus 1 divided by R34. So now that the circuit is series circuit like that, I can find the total current in the circuit, or I can find the voltage drops across each of the resistors. Then I can go back to the original circuit and look at the parallel branch, and I can find the currents that flow through each of the resistors. That is the general idea of how we deal with those compound circuits. Now I wanted to say a few words about the instruments that are used to measure potential difference, current, and resistance in a circuit. The voltmeter is the tool that's used to measure potential difference between 2 points in a circuit. The way that the voltmeter is connected to the circuit is always in parallel, and the voltmeter has very high resistance. The reason for the high resistance is that will result in a very small amount of current from the circuit going through the voltmeter, which leads to much more accurate measurement of the potential difference between 2 points in the circuit. If I want to measure the current in the circuit, then I will use the ammeter, and I will connect this tool in series in the circuit. The ammeter has a very low resistance because I want to generate very small or as small as possible voltage drop across the ammeter, and therefore that will not disturb the current measurement in the circuit. Finally, if I wanted to measure the resistance of a portion of the circuit or an element in the circuit, I would use an ohm meter, which connects in parallel to the circuit and has its own power source. So when the ohm meter is hooked up to the circuit, it creates a mini circuit around the portion where I'm measuring resistance, and then this mini circuit has its own small current, which allows the ohm meter to measure resistance. Another useful quantity related to electric circuits is the power consumed in a circuit. The power consumed in a circuit is calculated as the product of voltage and electric current, and it's measured in watts. If I know the power that's consumed in a circuit, and I also know the amount of time that for which this power was consumed, If I multiply the two, the power and the time, then that gives me the amount of electrical energy that was used by the circuit. So the amount of electrical energy is the product of the power and the time for which the circuit was used. The units in which electrical energy is measured are watt-hours or kilowatt-hours. And now if I know the price per kilowatt-hour, I can also calculate how much it costs to operate that circuit. And this, of course, applies also for power tools, for which the power rating is known, for electrical appliances, and so on and so forth. And so when you're paying your electric bill, for example, you are paying for the amount of energy that you've used per a certain amount of time. And so when you open your electric bill, the reading there is in kilowatt hours, and then you know the price per kilowatt hour. So when you multiply the used energy amount by the price, you will see how much you have to pay for your electric bill. This concludes the lecture on basic electricity.